Quantum computers explained in 10 minutes, the mind-bending future of computing. What if I told you that the future of computing won't be faster processors, more cores, or smarter algorithms, but a completely different kind of computer, one that uses the strange laws of the quantum world? You might have heard that quantum computers can solve in seconds what would take supercomputers thousands of years. Sounds like science fiction, right? But this isn't fiction anymore. Quantum computers are real, they're being built right now, and their potential is so massive that some scientists say, once they work at scale, they could reshape entire industries, from medicine and energy to cryptography and artificial intelligence. So in the next 10 minutes, let's explore what quantum computers really are, how they work, why they're so powerful, and how they might change the world forever. Part 1. The limits of classical computers. Let's start with something familiar. Your phone, your laptop, and even the world's most powerful supercomputers all work using bits. Each bit is either a 0 or a 1. Everything we see, the photos, the code, the videos, are just gigantic combinations of those zeros and ones. This system has served us incredibly well for decades, but there's a limit. As we make transistors smaller and smaller, now thinner than a strand of DNA, we're reaching a point where the weird rules of quantum physics start to interfere. Electrons can tunnel through barriers, signals become unstable, and information gets fuzzy. In short, we're about to hit the wall of classical computing. To go further, we need a completely new way to think about information itself, and that's where quantum computing begins. Part 2. Enter the qubit. At the heart of quantum computing lies a simple yet mind-bending idea. Instead of bits, we use qubits, quantum bits. A classical bit is like a light switch, it's either on or off. But a qubit, it's like a light that can be both on and off at the same time until you look at it. This bizarre property is called superposition. Picture flipping a coin. While it's spinning in the air, it's not heads or tails yet, it's both. Only when it lands, when you observe it, does it become one or the other. That's a qubit in action. This means that while a classical computer can only represent one state at a time, a quantum computer can represent many possible states simultaneously. That's the key to its extraordinary potential. Part 3. Entanglement, the quantum connection. But superposition is only half the story. The real magic happens when qubits become entangled. When two particles are entangled, they share a mysterious link. Change one, and the other reacts instantly, even if they're separated by light years. Einstein called it spooky action at a distance. In a quantum computer, entanglement allows qubits to work together as a unified system. Instead of acting independently like tiny switches, they form a complex web of possibilities. This gives quantum computers a kind of collective intelligence where every qubit carries information about the others. So, while 4 classical bits can only store one combination at a time, 4 entangled qubits can represent 16. With just 50 qubits, a quantum computer could represent more states than there are atoms on Earth. And at around 300 qubits, it could, in theory, hold more information than there are atoms in the entire observable universe. That's not speed, that's parallel universes of calculation. Part 4. How it actually works. So what does a quantum computer look like? It's not a tiny laptop or a black box full of wires. In fact, most quantum computers today look like futuristic chandeliers, golden towers hanging from the ceiling inside sealed glass chambers. Inside those machines, qubits live in incredibly fragile states. They're built using superconducting materials, trapped ions, or even photons. To keep them stable, scientists cool them down to nearly absolute zero, that's colder than outer space, around -273 degrees Celsius. At those temperatures, the laws of quantum mechanics dominate. Qubits are manipulated using microwave pulses or laser beams, and the result of their interference is what gives us the computation. A quantum computer doesn't calculate step by step like a normal one. Instead, it explores every possible path at once. Then, through interference, All the wrong answers cancel out, leaving only the right one. It's like asking the universe itself to compute for you. Part 5. Quantum algorithms. Of course, this strange new hardware needs equally strange software. Quantum computers don't run your everyday programs. They need quantum algorithms designed to exploit superposition and entanglement. The most famous one is Shor's algorithm. It can factor enormous numbers exponentially faster than any classical computer, which could break nearly every encryption system protecting online banking, emails, and even national security. That's why quantum computing has governments racing to develop new quantum-proof cryptography. Then there's Grover's algorithm, which can search through unsorted databases far more efficiently. While that might sound small, it could one day revolutionize AI, search engines, and pattern recognition. In short, quantum algorithms aren't just faster, they rewrite what computation even means. Part 6. The possibilities. So, what could all this power be used for? The possibilities are almost limitless. Drug discovery. Today, simulating even a single protein molecule can overwhelm supercomputers. A quantum computer could simulate the behavior of molecules at the atomic level, leading to new medicines, vaccines, and treatments discovered in days instead of decades. Climate and energy. They could help model global weather patterns, optimize renewable energy systems, or design ultra-efficient batteries. Finance. Quantum systems could instantly calculate risk, optimize portfolios, and simulate economic behavior on a global scale. Artificial intelligence. Quantum computing could dramatically accelerate machine learning, enabling models that learn in ways classical systems can't even imagine. In essence, quantum computers could become the ultimate tool for solving problems we don't yet have solutions for. Part 7. The challenges. But there's always a but. Quantum computers are incredibly fragile. Even the tiniest vibration, heat, or electromagnetic wave can destroy their quantum state in a process called decoherence. Keeping dozens, or someday thousands, of qubits stable long enough to perform complex calculations is one of the hardest engineering challenges humanity has ever faced. We also need powerful error correction systems because qubits are noisy and prone to mistakes. To create just one logical qubit that's stable and reliable, we might need thousands of physical qubits. So yes, we have working quantum computers today, but they're still in their infancy, with limited qubit counts and short coherence times. Think of them as the vacuum tube computers of the 1950s. Incredible breakthroughs, but only the beginning. Part 8. The quantum race. Despite these challenges, a global race is underway. IBM, Google, Intel, and startups like Rigetti and IonQ are pushing the limits of quantum design. Governments from the US to China are investing billions, and entire research institutes are being founded to chase quantum advantage, the moment when quantum computers can consistently outperform classical ones in useful tasks. Some experts say that might happen within the next decade. Others believe we're still 20 years away. Either way, once we get there, the world won't look the same. Conclusion: quantum computers won't replace your laptop or your phone. They're not meant for emails or Netflix. They're meant for impossible problems, the kind that shape medicine, energy, climate, and maybe even the nature of reality itself. Because here's the thing: quantum computers don't just calculate faster, they calculate differently. They use the universe's own rules, superposition, entanglement, and probability, to unlock answers hidden deep within nature. The quantum revolution has already begun, and when it reaches full scale, it won't just change computing, it will change everything. If you enjoyed this video, don't forget to like, share, and subscribe, because the future is quantum.